Hey everybody, can you guys hear me okay? Good, awesome. Yeah, first of all, I just want to say thank you guys all so much for being here at Avalanche Summit and for coming out to the talk. It was great to see a lot of you guys last year, and it's great to see everybody, or a lot of people back this year. And yeah, I'm really excited to share with you guys some of what we've been building for the past year on Warp Messaging. We're really excited about it, and I'd say that my goal for this talk is that at the end of it, everyone will actually understand it, is the goal. So if at any point in the talk you guys start to lose me, feel free to raise a hand. Would love to take questions in the middle and just go through it and make sure that I'm not losing track of anybody at any point. So feel free to interrupt. But what we're going to talk about today is what is the vision and why is Warp Messaging important? How does Warp Messaging actually work? And then how do we actually integrate Warp into the EVM? So first of all, for the vision, what are we doing here? The goal here is essentially to scale blockchains. And blockchains, people have tried to do this on a single chain for a long time. And this has led to various trade-offs being made. And a large part of the reason to do this on a single blockchain is that it guarantees that you get atomic composability. When you have a single blockchain with a single piece of state, you can always guarantee atomic composability. You can perform multiple actions and decide whether to commit all of them or whether to abort and get rid of all of them. And this is really critical for applications such as arbitrage on DeFi applications, where you want to be able to perform multiple trades. And if they're all profitable at the end of the day, then you might commit all of them. And if it turns out that they're not profitable, you abort everything. And so atomic composability has been one of the killer features of blockchains. And it's what's led people to try and integrate as much as possible into a single chain and scale it up as much as possible, the highest performance possible. But at the end of the day, what we've found is that as much as you do that, you're always going to have the capability for demand to exceed the capacity. You're going to see rising prices, you're going to see failures, and so the alternative goal is to actually try and create a multi-chain ecosystem instead. And so that's what we're doing with Avalanche, and that's why cross-chain communication between all of the different blockchains that you might build becomes so important. So how do we do this, and how do we make it so that each individual blockchain and all of these subnets actually add value? The way that we think about this is that if you're going to launch a blockchain, you have the choice between being a layer 1, launching your own protocol, and being a blockchain on top of a network of blockchains. So if you choose to be a part of a network of blockchains, ideally you are gaining value from the fact that you can interact with all of the other blockchains there through some sort of inter-subnet communication protocol that enables not necessarily atomic composability, but a form of looser composability, where you can scale, move applications into different places, but still have some notion of I am better off being here because I'm part of this broader ecosystem, and I can somewhat seamlessly interact on one chain and another and perform multiple different actions across subnets. Does that all make sense so far? Yeah? All right. I see some nodding heads, so I'm happy with that. So what is Warp Messaging? Warp Messaging is the cross-subnet communication protocol on Avalanche that we've built out over the past year. And the way that it works is essentially the P chain serves as a membership chain on the Avalanche primary network. So this membership chain essentially says, this is the validator set of the primary network. This is the validator set of every different subnet that's on Avalanche. And every subnet on Avalanche is also every validator on a subnet on Avalanche is also a validator on the primary network. And this means that they all have read access to the P chain. What this means is that because you have read access to the P chain, you can also read the validator set of every different subnet that's out there. And so one of the tenets of cross-chain communication is that in order for two chains to communicate across two different sort of validator sets or trust zones, you have to have some third party that's going to serve as some third party is needed to serve as to authenticate what happened on chain A in order to communicate to chain B. This is simply a requirement. There was an interesting paper sort of summarizing this, but it's sort of self-evident as well. So what a lot of bridging protocols do is they actually go ahead and have some multi-sig, which is more secure than just having a single signer, but it's a compromise in decentralization and potentially a compromise in security as well. So the goal of cross-chain communication protocols is to get the best possible security that you can. And so Warp relies on the fact that the P chain is already validated by everybody to essentially use that as this trusted third party. And so because you're using this sort of maximally decentralized membership chain that gives you insight into the validator set of every different subnet that's out there, you can sort of use it as almost like a light client that tells you the validator set and this trusted third party without taking on different trust assumptions in order to set up a bridge between point A and point B. So that's how we use the P chain. Does that make sense to everybody? Yeah, okay. Seeing the more nodding heads. So what we do on the P chain is we register all of the BLS, we register all of the validators there. And in addition, what we do is we register a BLS public key along with a proof of possession that says, yes, I in fact hold the BLS private key that corresponds to this. And so once we have that BLS public key, in addition to having the subnet validator sets for every different subnet that's out there, we also have BLS public keys attached to each one of those individual validators. And this actually gives us enough in order to authenticate a message that's been signed by the participants of another subnet. And this is really all that we need in order to build Warp. And actually at the most basic level, the primitive that we released on Avalanche Go, which Steven can tell me exactly when that was. I think that was November? December, okay. The actual primitive has been in Avalanche Go since December. And all that it really takes is having the BLS public keys registered to the primary network on the P chain, and then the ability to verify a message. So what that looks like is you have, as subnet A sending a message to subnet B, or more aptly, chain A sending a message to chain B, chain A's validator set is registered on the primary network, and you can see every single BLS public key is stored there as well. And this means that if the validator set of chain A decides that it wants to send a message, whether that's a block hash or some other payload format, whatever it wants to be, it's actually defined by the VM. All that it has to do is those validators, after they've accepted some block, they've already come to consensus, they all sign that message that they want to deliver. And then when it goes to chain B, all of the validators of chain B can actually authenticate that this message was actually signed by the validator set of subnet A or chain A. And this gives you really the best possible security, because if you were using any other form of third-party bridge, if the validator set of that subnet were already compromised, the bridge would essentially be compromised too. And so by actually using the exact same validator set of the chain, you're getting the best possible security and verifying the message directly. So that's all that it takes. Is everybody following that? Yeah? Okay, great. So that's all that Warp messaging really is. And then the next piece is how do we actually go ahead and integrate that into the EVM? And this is where it starts to get more fun. I did a talk on this a couple weeks ago, and the way that I explained integrating things into the EVM was I showed a 1.5-minute YouTube video of somebody who was fitting, I don't know if you guys have seen this, but there's a video of a woman who is, it's a reaction video, and there's somebody who's fitting various pegs into a square hole, and she fits all of the shapes into the same hole, the same square hole, and you know, there's a sphere, there's a cylinder, everything, and everything goes in the square hole, and the woman's face slowly droops as she gets sadder and sadder and sadder, and this is how I like to describe my job sometimes. Because the EVM is difficult to integrate things into sometimes correctly. And if you look out at a lot of different protocols that have integrated various precompiles, us included, it has led to a significant number of hacks. And so when we build this protocol out, we'd like to make it as lightweight as possible and keep that whatever computation is done by the EVM, whatever we have to integrate into there, as small and as lightweight as possible to keep our trusted computing base incredibly small. So what we do is we make this as simple as possible and make as few promises as possible and then build a layer on top. If you guys got the chance to go to Michael Kaplan's talk today, it was a few hours ago, he talked about the protocol that we're actually building on top. But Warp messaging at the very base level, all that it gives you is signing of a message from subnet A and the ability for subnet B to actually verify that message was signed by subnet A. So it doesn't give you ordered message delivery. It doesn't give you replay protection, nothing. All that it does is it gives you the ability to verify a message. If you want to build any additional properties, you have to build them on top. And so we'll be doing that with Teleporter, the protocol built on top. I'm not sure what name we're going with there. But the way that we actually implement this in the EVM is using a precompile, which we've talked about a lot, and we're using this a lot in evergreen subnets as well, in order to build various functionalities like a transactional allow list, contract deployer allow list, and Warp is going to be one of the most differentiated ones. And what it's going to do is give the EVM an ability that it doesn't have before, which is to look up the validator set of some subnet, let's say subnet A, and actually verify a signature based off of that. So you wouldn't want to implement this in Solidity, and even more so, you actually don't have access to the state of the P chain in Solidity or in the EVM in general. And so we have to do a couple of jumping jacks in order to make this work. And so the way that we actually do this is we've decided to introduce this notion of a predicate into the EVM. So we actually use EIP 2930 access list transactions. So if you guys are familiar with EIP 2930, what it does is it allows you to specify various storage slots. And in those storage slots, you can load and say, this storage slot I'm going to use in the context of my transaction, and it will pre-warm the cache knowing that that will be used in the course of the transaction's execution, and so it will make it cheaper for you to access it. And so this gives you the ability to provide some sort of a hint into the EVM in terms of what that transaction execution is going to look like. And so we, as I like to call it, have bastardized this in order to create a notion of a predicate. And so a predicate, if you guys are familiar with computer science, or if you guys are not familiar with computer science, it's as simple as make sure this thing is true. That's all it is. And so we actually use this access list in order to encode the signed message from subnet A. And all that this means is that we have some message that adheres to the Avalanche Warp Messaging format. And when we are verifying the block, we'll actually look at all of the predicates beforehand. So we'll read all of the predicates and verify them using the P-chain state. Look up the signatures and validate that the signature is valid. And then the actual execution inside of the EVM doesn't need to do anything with the P-chain state whatsoever. So from the perspective of the EVM, there is no outside computation. It's just this predicate that is actually kept completely separate, and there are no external calls whatsoever. So this gives us a nice sort of clean architecture, and that we don't have to introduce any new app codes or functionality or external calls made from the EVM itself. And we can actually do all of this in advance and know exactly what the result is. And the reason that we have to do this is, one, it makes the code relatively nice in that we don't need to introduce any external calls into the EVM itself, or while the EVM is executing a transaction or executing a block. It can all take place beforehand. And the other interesting thing here is that we need to be able to reprocess the block at some point in the future. So we're running blockchains, and what that means is that we have to actually be able to reprocess and verify the blockchain. If somebody wants to enter the network, they should be able to fetch all of the blocks and verify all of them. And this creates one small problem for us in Warp, because Warp messaging inherently relies on the state on the P-chain. And the P-chain is not and should not ever be an archival node that gives you an archival complete history of the P-chain state. If it were, it would be, if that were a requirement, that would add that overhead to the network forever. Everybody would have to be able to serve that. And so what we do instead is we only serve the current state, and we keep reverse diff layers that give you the ability to compute the state some number of blocks ago. And we can always take these diff layers and compute the state, in blocks before. So what this means is that if we verify a message at, let's say, in the subnet EVM at block height 1,000,000, that might depend on the P-chain state at block height 1,000 on the P-chain. So if we do that, and the P-chain advances to block height 2,000,000 at some point in the future, we should still be able to verify that same block on subnet EVM. But if the P-chain state has advanced 1,000,000 blocks into the future, we would now have to compute all of those reverse diffs in order to calculate the validator set. And to do that would be very, very expensive. And if there were a large number of warp messages in every single block, we would have to, perform a lot of these diff layers in order to calculate the validator sets. So that is problematic. And the way that we solve this is to say, instead of that, what we do is we include this predicate, which we know will be verified at the time it's accepted by the network. And this means that when you're joining a new network, any block that's already been accepted by the network, the predicate was already validated before. And so instead of requiring that you look up the P-chain state in order to figure out if a warp message was valid or invalid, you can just assume that anything that was encoded in the predicate is valid. And so you completely remove the need to look up the P-chain state when you're reprocessing historical blocks. Anything that has already been accepted by the network, that the network actually verified that predicate in advance. So this works out very nicely. There's one other approach that's actually taken on HyperSDK that works as well, which is to staple the results of warp message verification to the block itself, which this is also getting around the same problem of at some point in the future, you won't have the P-chain state, you won't have the validator set, and you need some other way to know whether this warp message was valid or invalid. And so in this case, if you're stapling the results to the block, what you can do is you can sort of staple this message was valid at this point in time, this message was invalid. And so if you're ever reprocessing that block, you can use those stapled results to actually see exactly what the result was. Is this all making sense? Awesome. Yeah, thank you guys so much. That's warp messaging in the EVM. That's all that there is to it. So I hope that made sense. Yeah. Thank you guys for coming. Does anybody have any questions? Yeah.
We've learned in a previous talk today that the warp messaging goes through a relayer, and everybody could also be a relayer. How is a relayer bound to a validator? Is every validator automatically a relayer, but one can also be a relayer but not a validator? Or how is it organized?
Yeah.
And how is the gas fees split across both parties then?
Yeah, that's a great question. So warp messaging itself, as it's integrated into the EVM, only provides you one thing, and that is the ability to verify a message coming from another subnet. That's it. And so this means that we don't actually relay the messages, which is why we're building this relaying protocol teleporter on top of it. It also does not take care of the execution of the messages when it's received. So that is also taken care of by a protocol built on top instead. So this is going back to that point about minimizing the trusted computing base of how much computation you have to integrate into that precompile and making that as secure and lightweight as possible. So what we do instead is in Teleporter, it can actually provide all of these properties. So Teleporter, a relayer that's run off-chain, can observe some message and then query all of the validators, say, hey, please give me the signature that corresponds to this message. You should be willing to sign it because it just happened. And all of the validators should sign that message, send it to the relayer, and the relayer should essentially take care of saying, okay, I aggregated a signature, it's valid at this point in time, and relay that message to subnet B or chain B. The relayer at that point in time has to define its own semantics for how it should take care of paying for gas. So in Teleporter, the protocol from the talk that you mentioned today, the way that this is being handled is that you pay for fees on chain A, the originating chain that's sending a message, and Teleporter will actually make sure that it's receiving a high enough fee in order to be compensated, and it will deliver the message for you, and it will pay for the fees on the other end of the computation. You could also design different protocols on this. I think there's a lot of different interesting things that you could build on top. One example of this is that a lot of other protocols only rely on a signed block hash. And once you have that, you can prove out everything from there. You can provide the block data and say, here it is, here's the actual block. And you can also, if you have one block hash that is signed, you can actually prove, okay, here's the parent hash and reverse compute everything from there. And if you want to do something like that, that's actually what Layer 0 relies on as well. So you could actually integrate Avalanche Warp Messaging to provide just the block hash and then build out all of these other protocols with the best-in-class security that you could get. It's another very interesting approach. Sure.
I'm just a layman, but in terms of like the...
So layman's talk.
Yeah, so like could someone use warp messaging? Let's say they're building like a DeFi protocol on Subnet A, and Subnet A validators don't also validate Subnet like D or HFIJ, but they want to like take out a loan through like, maybe it's like the same DeFi protocol or like a different DeFi protocol but integrated the other. Like take a loan against assets on a different chain completely. Mm-hmm. That's something that could, like this could enable that.
Yeah, this is just cross-chain communication. And so if you can attest, yes, these funds are locked on this other chain, you can then take out a loan against that and have some protocol on the chain that you're taking out a loan and say, yeah, I will pay back this chain, and then you'll release the tokens back to me on the other subnet. Or you could even move funds from one chain to another, lock them there, do some other stuff with it, do whatever you might want. It's the application built on top, which I stay very far away from. But yes.
Can certain subnets block incoming messages from other subnets if they so choose, or can they also implement like an allowless functionality to only get messages from certain subnets?
Not currently. But yeah, you could do something like that. So that's up to the VM. So in the PR that's up right now for Subnet EVM, there's no functionality to restrict which subnets can actually send you a message. It is up to the communication protocol built on top to decide what messages are actually going to have meaning. You know, if you get a message from some other chain, that doesn't necessarily need to trigger anything. So there maybe is just no contract that you receive it from this other subnet that you don't care about, and you say, I don't care about that, just throw it away. It's perfectly valid. It would also be interesting to say, you know what, actually, I'm not even going to verify messages from specific subnets. That does become part of the state transition itself, so it becomes part of the VM itself. So that would have to be changed or upgraded through an actual network upgrade, so that there's like a canonical definition of what is valid at a certain point in time.
Hi, there is some place with documentation about everything, because I'm going to forgot everything this night with a couple of drinks.
Hope to share some of those drinks with you. And there's a PR up on Subnet EVM right now, and there's a README in it that documents all of this stuff. So there should be a pretty clear explanation of how Avalanche Warp Messaging works, how it works on the P chain, as well as how it's integrated into the EVM with the predicate style that I talked about.
Hi, thank you for a great talk. I just wanted to validate with you, did I get it correctly, that to make, let's say, a subnet that we are potentially running to use and interpret the messages incoming from the other subnet, we need to, let's say, develop additional precompile as extension to the virtual machine which is running our subnet, and that's the way to, let's say, use and interpret the messages in our business logic. Is it correct?
Yeah, so there's the PR app right now, which is adding this precompile for you, which is basically taking care of specifying this predicate and making sure that it's called and verified before the block execution actually starts, to make sure that you're validating these messages and nobody can lie to you about BOS signatures or anything along those lines. And it also defines a payload format, essentially, which specifies a source chain, a destination chain, a source address, and a destination address as well. So this means that the actual way this works is a specific contract would call the precompile, and it would emit a log. That log gets emitted, and then all of the validators, when they see this block, they look at that log and they say, okay, I'm going to add this this unsigned warp message to my database of messages that I'm willing to sign. So then it would allow it to be aggregated, and on the other side, somebody else has to define the logic for accepting this message. So Subnet EVM will be compatible with Corey with the C chain. So once this is out, you'll be able to send warp messages between any different EVM chains on Avalanche. They'll have to enable this warp precompile. It will be optional. But yes, you'll be able to verify messages however you want. And if anybody's building a custom VM, they would have to make sure that they comply with the same architecture. So one of the ways that makes this a little bit funny is that you could actually do this in order to have cross-chain contract calls. So you can have a contract that says, yeah, I want to send a message to this address. And define some payload data that's maybe ABI encoded by a Solidity contract. And if you are then talking to something that's in COSM WASM, for example, if they don't have the same primitive that enables you to parse like ABI encoded data, you have to have some sort of adapter in between to say, what does it look like to call a COSM WASM contract versus calling a Solidity contract? So inside of the EVM, all of this logic makes sense and it's pretty nice. As soon as you go to different VMs, it becomes a little bit more complicated. You have to add these adapters on in the middle in order to authenticate what that data actually means.
So does it mean that as soon as that pull request will be merged, that the standard EVM of Avalanche will be able to, let's say, receive that message, and that message could be received by Solidity smart contract that we are developing and deploying?
So it'll be, the way that it actually works is that it won't be received by a contract exactly, but the contract will actually have to call to view what the predicate is. So it'll be actually a view function where you can say, read whatever the verified warp message is from this transaction. So you'll be able to encode one in the transaction and then look it up. And so a contract will actually have to verify it and then provide the logic to say, yep, I verified this message. It is in fact intended for me. Therefore, I know that this was called on other chain A. Intended for me on this chain. Make sure that that is actually the chain that I'm on right now. And then define its own execution logic for that, which could be, actually perform the call itself, or it could be some other completely different logic. It could be storing that call to be used later. That call could even include in the payload itself the amount of gas that is intended for the call, and execute with exactly that amount of gas in order to have like a very, very similar semantics from chain A to chain B. Yeah, and once that PR is merged, it won't be that it'll be active immediately on every subnet. It'll be similar to the precompilers that exist today, where you actually have to go ahead and enable them. So it's very easy. You can enable in the Genesis, and you can also enable it through a network upgrade. So as soon as that's released, it's obviously a completely new functionality. So any subnets that exist now, they'll have to perform that network upgrade in order to enable Warp, and we'll schedule a network upgrade in order to enable it on the C chain as well, so that people can communicate seamlessly from the C chain to subnets and vice versa, as well as between different subnets.
Thank you. And if I may, the last question. So you mentioned a few times about the payload of the warp message, and is it? I mean, the question is about the data model behind that payload. Is it somehow restricted by a specific scheme, or it can be defined arbitrary scheme for that data model of the payload?
Yeah, so the only part that's defined is this source chain, source address, destination chain, and destination address. The payload format itself is arbitrary bytes, so you can specify whatever you like. So it could be, you know, ABI encoded data to be delivered and actually executed on some other contract, or it could be anything else that you might want.
Hi, so let's say I have a smart contract on one of the subnets, and I get a message from some other subnet. How do I know which subnet sent that message?
Yeah, so, sorry, could you repeat the question actually? Just to make sure.
Let's say I have a smart contract on one of the subnets,
Yeah.
and some other subnet is sending me the message. How can I confirm it's the subnet I accept or something like that?
Yeah, so the message itself is going to include the source chain that sent the message. So a subnet should never sign or a validator should never sign a message on behalf of a different subnet. So if an event occurs on subnet or on chain A on subnet A, then it should sign that message, and included in that message will be the source chain itself. And so when you're receiving that message, you can actually look in the message itself and say, this message originated on chain A. Yeah, thanks for the question.
Will all of it apply for C chain? So like, would it work on C chain both ways?
Yeah, it'll work on C chain in both ways. Actually, one piece that I didn't talk about as much is exactly how it'll work for C chain to subnet communication. It's not a huge overhead necessarily, but because the C chain is on the primary network where everyone is already a validator, it is the network that it is the subnet that has the most validators, and it would be the most expensive to verify multi-signature from there, as well as looking up the validator set from the primary network. So the way that we've actually made this a little bit more efficient is that if the C chain is sending a message to a subnet, if the validator set of that subnet is already compromised, like let's say you're running 10 validators, if 6 of them are already compromised, then that subnet is already compromised. Since those validators are also already validating the C chain, the way that this can work really nicely is that instead of requiring a signature from every single validator of the primary network, in order to validate the message instead, it will require a threshold of signatures from the subnet that is receiving the message itself, because you don't actually need a signature from every single validator there. It doesn't really change the trust assumptions whatsoever if you are having signatures from the validator set that from your own validator set, since they would already be able to cause arbitrary things to happen if they were corrupted. So this was a nice optimization that we added. So it'll be fairly straightforward and actually just as cheap to verify a message from the primary network to a subnet as between subnets of the same size.
Does the message have some sort of a state, whether the message is actually delivered or whether the execution of that message is rightfully executed, or how is the state managed?
Yeah, so at the warp level, it is only providing the verifiability of the message. There's nothing stored in the state, and this is an explicit design decision to try and make it as lightweight as possible. So for our teleporter, the protocol built on top is going to be Solidity smart contract that actually will store messages if they, for example, are failed to deliver. There will be a system for having receipts of messages, as well as, like I think somebody mentioned, in order to talk about how will fees work on the subnet, there will be receipts that actually get sent back to the originating subnet, so that the person who delivered the message can actually get paid for proof of delivery after it's been executed. So the way that this will work with Teleporter is that these contracts will actually be executed, or sorry, these calls will actually be executed on the receiving chain. The payload format itself is actually going to specify an amount of gas to use. And so that amount of gas will be used in a low-level EVM.call operation, or yeah, an EVM call operation. And it'll be used with that exact amount of gas, as well as the exact input data that's specified by the message. If that message fails, that it can actually be stored in the state as well, if you like, so that you can retry that message at a later date and pay for it at that point in time. Thanks. Yep. Awesome. I think that's all the, oh, maybe one more.
Test. One more layman question. The difference between warp messaging and IBC.
That's a good question.
Oh, sweet.
It's not a short question. IBC is a very different protocol, and you could actually build IBC on top of something similar to Avalanche Warp Messaging. The main differentiating factor of Avalanche Warp Messaging to me is that it's using the P chain for communication across any two different subnets. And so what this means is that you don't need to set up a permanent or a connection between two different validator sets, whereas in IBC, in order for two different Cosmos zones to talk to each other, you have to essentially set up a light client from point A to point B. So it's a much more point-to-point communication system that you could actually also build on top of Warp and use Warp messaging and these signatures in order to have a guarantee that a specific block hash was confirmed and accepted by a specific blockchain. You could still set up the exact same frameworks on top of Warp messaging, but Warp does not necessarily require the same light client point-to-point communication because it's actually using the P chain instead in order to provide the validator sets. That's a short question or a short answer to a much more complicated question, but it's the best I can do without running much more over. But thank you guys so much for coming. I'll be around after if you guys have more questions. But yeah, thank you guys so much for being here.